Hey everyone, very good having you all. Very excited about this live stream, Twitter Space / live stream. So today we will be discussing how to mitigate the threshold trust assumption in MPC and also threshold cryptography in general, prospectively sort of threshold FEGE even. And we'll have pretty amazing lineup of guests from the use cases side from MPC, but also on sort of those mitigation strategy side. Let me go sort of just briefly over the names. First, or if I myself, I'm Luis. I'm a product manager with BrainBot, working on Shatter Network, which is a threshold encryption DKG mechanism, which we primarily apply one for encrypted mempools to protect against front running and real-time censorship, currently on Gnosis chain, but prospectively on hopefully on Ethereum L1. And also the other use case is for voting, so encrypting the real-time results of DAO voting, and they were natively integrated into Snapshot. So then we'll have Tristan, from co-founder of Nillion, which is an amazing MPC project, working on crazy use cases to do with MPC, advanced MPC. We'll have Professor Sebastian Faust, who is leading the applied blockchain or chairing the applied blockchain department at Technical University Darmstadt, one of the leading sort of technical universities in Germany. We'll have Shelvin, who is the lead researcher at Fala, and Fala is doing amazing work with TEEs and also in this space of sort of protected or truly autonomous agents via TEEs with Flashbots and other amazing partners. And then we'll have Andreas, who is a postdoc cryptographic researcher at BrainBot and Shutter. But I also want to leave everyone sort of from themselves to introduce, maybe starting with you, Tristan.
Sure. Hey guys, I'm Tristan. I'm a co-founder at Nillion. At Nillion, we're building what we call the blind computer, which basically has the goal of trying to make it easy to build with all of these privacy enhancing technologies. Right now, you tend to have to be, a cryptographer, even a PhD to implement or use a lot of this stuff at the application layer. And we're trying to solve that. And I think the topic of today's discussion is a very important piece of that because a lot of the tech that we use is MPC and requires these sort of threshold assumptions.
Thanks. Yeah. Maybe Sebastian, do you want to go next?
Yes, so thanks a lot, Luis, for the introduction. So I'm a professor at Technical University in Darmstadt, and I'm working mainly on cryptography. So recently we worked a lot on applying these cryptographic techniques or cryptography to blockchains. For example, we started working a lot with the layer 2 protocol. So we designed some state channel network called Perun. And we also worked a lot on other cryptographic building blocks, like analyzed cryptographic wallets together actually with Andreas. Recently, so also we developed this MEV, or the crypto essentially behind this Shutter network, which was a nice start for us to get into MEV protection. And recently we are continuing working on this and addressing some of the shortcomings of threshold cryptography for MEV protection.
Thank you. Maybe Shelvin next.
Okay, thanks, Louis. So, hello guys, I'm Sheldon from Fala Network, and I'm the lead researcher of the company. And what Falas do is that we have host a decentralized network which all consists of all the TE nodes. And actually, recently we are exploring the latest version of TE, which is called the Intel TDX. And also, we are doing some research on the support of like TE GPUs. And also we are exploring a lot of use case of the TE, for example, including use TE for MEV and also like use the TE GPU to run the AI model and also use to use it with the AI agencies. And also, I think a very important direction we are talking about today is to use TE with the existing like cryptographic based solutions like MPC and also the case, so it can be used to strengthen the all the like capability of the existing cryptographic algorithms. Yeah.
Thank you. And then Andreas, last but not least.
Yeah, hi. I'm Andreas. I have a background in cryptography, so I did my PhD in Sebastian's group in cryptography. I worked mostly on cryptographic wallets and threshold cryptography. I did then a short time as a postdoc, and recently I joined Brainbot to work on Shutter as well.
Thanks, perfect. And maybe just leaving it here with you, just very briefly, Andreas, what is actually threshold cryptography and what is MPC? Kind of just as a brief explainer, I think would be good for everyone listening who's not familiar.
So threshold cryptography kind of allows you to distribute a cryptographic task. So for example, you have threshold encryption, where you have like a standard encryption scheme, but the decryption process is distributed. So it's executed by many parties. Or you have threshold signatures, where a signature can only be generated if many parties come together and execute the generation process together. And typically, that's where the threshold comes into place, that you need a certain threshold out of a set of parties to actually compute this task. And MPC is more like a general purpose kind of computation, I would say, where you can essentially compute any function in a distributed manner.
Thanks. Yeah. And Tristan, so that's sort of the theoretical side more so, but as Nilian is really active in this space and building our actual use cases, what are some of the amazing use cases that the MPC can enable, or which ones are you most excited about kind of being also practical in the in today maybe already, or at least near future?
Yeah, I think it's an interesting question. I mean, I think that MPC has had a hard time getting to production, right? Like we still talk about the sugar beets auction as like and hold it up as a very important piece of real world adoption. But I do think that that's changing, and a lot of that is coming from the crypto world. You have the deployments like what has happened over at WorldCoin with kind of massive numbers of these Iris things running directly in GPU. What we are primarily working on is kind of general purpose MPC, but really a lot of our research focuses on AI use cases. Some of these AI use cases will be further out in the longer term, right? Like real inference over big state-of-the-art models is going to take a long time to be performant. But in the nearer term, we are already seeing people who are building things that we think are useful in that domain, notably things like private RAG, retrieval augmented generation over things, or using smaller models like some of the work we did recently, which uses smaller BERT models for sentiment analysis over sensitive data. So really we see use cases for MPC, PETS as a whole, but MPC to be finally moving from research to production.
Cool, yeah. And I think it's really impactful because, I mean, in a way, public blockchain allows sort of the verifiability of applications, right? And it allows auditability. But a lot of, maybe even most, I would say, use cases of this technology are sort of hindered because of that transparency and because of that auditability. So I feel like sort of kind of finally privacy and private computing adding to that is the final is basically is the enabler of probably most use cases for blockchain. If you think about it, most every use case that's serious needs privacy, right? So yeah,
we call it kind of the white space, but yeah, I do think that a lot of people think about privacy as just this nice to have feature, and sort of our contention is that no, not only is it like necessary for a lot of, as you're mentioning, commercially viable use cases, but also it really expands the white space, like the possibility, the design space of what you can build using decentralized technology. And so, it's not just like a little, oh, we should have privacy on this. It's a nice to have feature.
Exactly. Yeah, fully agree. Yeah. But that leads us maybe to this sort of one of the blockers sort of for MPC and threshold cryptography, which is the trust assumption. Kind of comes with the is sort of inherent to threshold cryptography. So maybe Andreas, maybe would you want to just briefly touch on what that is again? So what is a trust assumption? Yeah.
Sure. Yeah. So kind of like I said before, like threshold cryptography, like you have a set of parties that want to compute some cryptographic function, and at least a threshold of these parties or some subset of those parties need to come together to successfully compute that function. But that inherently also means that if we talk about corrupted parties, how many of these parties are honest and how many are corrupted, that means that we can basically not guarantee any security if more than this threshold of parties are corrupted, because then these corrupted parties can always come together and just compute the function by themselves. So in threshold cryptography, we always need to assume for security that they are less than this threshold amount of parties that are corrupted.
Yeah, and it's sort of inherent, right, with how it works. And maybe just to dive one level deeper into the practicality. One thing I'm always thinking about is, and I just want to get a feel maybe in this group. So what is actually the threshold going to be? Sort of, is it going to be usually kind of like a 2 out of 3, or maybe is it going to be more like a 90 out of 100 nodes, or something kind of in between? Does anyone have an opinion on this?
Yeah, so we go out, and the architecture of our network is that, we have this side of the network we call the PETNet, the Privacy Enhancing Technology Network, but people can build their own clusters inside of that. And so as a application developer, right, you can choose to either use existing clusters that fit the security requirements you need or spin up your own. Going to market with that and actually selling people who are going to build on top of us, talking to enterprises and stuff like that, what we have seen is one, people care less about the size than I had originally anticipated. And two, the most successful offering we have been finding for people who are building these applications on us is actually not the fully delegated model, which is like, hey, we've gotten these very secure, trusted parties to create a cluster for you guys, come and use it. But rather, they want, if you think about the three stakeholders, an application, sort of the network, so all of the parties in the threshold, and a user, a lot of the things that people want to be building, at least on us these days, they are kind of letting the user be self-sovereign of the data, and then they want to be the one who is preventing the collusion. So they're actually one member of the party, of the threshold, right? So one party in the computation, but then they have other node providers who are preventing them from being fully custodial. And ultimately the user is the one who controls the permissions, right? So it's, even though it's the same threshold, right? Like the same number of parties, whether it's 2 of 3 or 3 of 4, whatever it is, we do find that there is a little bit difference when talking to the developers about whether they are one of the parties or not, and kind of how much control they have over it.
Interesting, yeah. So more asymmetric sort of setup there, yeah. It's pretty interesting. Yeah, and I think in general these threshold sets I think will scale, right? Hopefully with the technology. So I feel like the less they are right now, then the trust assumption is a bigger problem. But I'm hoping also, so for example, on the keeper set on our encrypted input for Gnosis chain, it's only 7 keepers so far. So it's I think a 4 out of 7 sort of threshold. But we purposely have designed the protocol in mind with scaling it a lot higher, first to sort of 21 nodes, and then hopefully to more like 200 nodes, such that then yes, on the one hand side, I think it's an extremely big sort of blocker. In general, sort of anything trust related in blockchains, I think is a big problem. But it's also, as it scales, I think it's going to become better and better. Yeah.
I think there's also like maybe I can jump in quickly if you don't mind. So I mean, like regarding this number, I think if you want to have like an open network where everybody can join, then I think it would be also nice to have something like that you actually stay anonymous, because the point is most likely that you want to protect against like somebody targeting some particular node to switch it off, the denial of service, or corrupting this particular node. So you would like to have this kind of technique where you actually don't know who are the current participants. So you have like a huge set of parties that maybe consist of like essentially like in Ethereum, where you have like, I don't know how many nodes there are, 32,000, but then you always have like a small set who are responsible for this. So it's very hard to shut it down. And I think also like in Threshold crypto, it would be ideal that you have like essentially tons of nodes holding or being responsible for holding some keys, but you always only select a small subset, and this small subset is going to be responsible then for like creating the next signature or doing the next block decryption or something like this. And there's actually some technique that is called like you only speak once. I mean, like Yozo MPC, which can do something like this. Unfortunately, it's way too inefficient currently. But yeah, so this would be nice to have, I think, if you want to do about large scale open networks.
That's very interesting. Sounds good. Yeah. And just one more question, kind of to Tristan, probably also in the room in general. How much of a problem do you see this kind of blocking right now, the advancement of it, or is it more so something that's kind of in the back of the mind? Or so for just one sort of anecdotal evidence is that we're definitely seeing on Twitter people are complaining. So when we talk about the encrypted mempool and Gnosis chain, Martin tweeted about it. There's some guy who's saying, well, what the hell is only like these 7 nodes that you're trusting? Like it's not even like decentralized.
Yeah.
So we definitely feel that as a kind of as a blocker from a communication perspective as well.
Yeah, so I think, and we obviously run into that as well, but ultimately the way that I see it is that that narrative is sort of looking at things from exactly the opposite lens. There's a lot of people, and there's a tendency in our space for good reason, right? We come from blockchains. If you run your own full node and you're doing things correctly, you can actually tell if anybody's doing anything wrong. Like there's this sort of like radical verifiability that is built into the technology from the blockchain side. That's not what you're going to get out of private shared state. Like distributing trust is not the same game as what you can do with the blockchain, and it never will be. So rather than looking at things from this sort of pure decentralization angle that blockchain brings to the table, I actually sort of like looking at things from the other way, which is that my contention would be that 2 kind of decent parties is like a threshold of 2 decent parties is, you know, orders of magnitude more secure than a single party from a trust perspective. Like a single party, there's no auditability there, right? The friction of coordination is zero, all of that stuff. If there's employees, if it's like a large industry, right? How many actual people have access to the data underlying without having any sort of overview of that? So if you think about it from, we are trying to mitigate the kind of pure centralization that exists for all of these structures that we are trying to build applications for, then every step forward is, you know, many like much more secure. And that's like the right way to be moving, rather than letting perfect be the enemy of good from the other angle. But I also do understand that, like, you know, every application, every user is going to have to make those trade-offs and trust assumptions for themselves, just like we do with blockchains today, right? Just like we do in the multi-chain world. And that legibility is one of the hardest problems that I think that pets are going to face as they sort of go to market and get more usage.
Definitely, yeah. I think it's totally correct. Yeah, kind of the sometimes people don't really understand where it's coming from, that we are moving from, that there are still a lot of centralized trust assumptions oftentimes, and then fully centralized sort of setups, and then yeah, fully agree, going from there to even to 2 nodes is so much better than yeah. Okay, cool. Yeah, and then maybe just kind of segueing into this topic of how can we address it already today? What is maybe sort of something that's relatively obvious, I would say, is kind of this bringing in TEE and combining TEE and TEs and threshold cryptography. So maybe just then handing it over to Shelvin. Maybe could you briefly say what is TEE and how and what is Fala in general working on? Don't have to relate it to threshold cryptography. Maybe just a more greenfield. What do you want to talk about you guys are working on?
Yeah. So actually, the full name of TE is Trusted Execution Environment. So actually, it's a hardware. You can just think it as a special hardware or special hardware security features. So, and actually the TE has been evolved for a very long time. For example, in the it's in like 2019 when we start the project. So the only available TE implementation is called Intel SGX. And recently, like there is more and more like solutions, including like Intel TDX. That's the next generation of the TE solution. And also there is something like AMD SEV, and also there is the TE GPU. So I think more and more TE hardware is being proposed with better performance, and they are much easier to use compared with the first version. And I think a very important problem that people want to combine the TE with MPC is to, I won't say solve, but at least to mitigate the problem, the risk of collusion. So I think let's just imagine like, what if we can run like the MPC node inside TE? So what will happen? So I think generally there will be two things. So the first is that although this MPC node operator, he is still running the program, but if you put the program inside the TE, then even he as the operator, he cannot see the real private key, his key share inside the MPC node. This is very important because this means, okay, so what he can do is that he must ask the program to do the signing things instead of like try to extract the keys and do something himself. And so this is the first part. So this is confidentiality features which bring by the TE. And I think on the other hand is that the TE has a feature of, it's called remote attestation, which means as a user, you can always like ask the TE hardware to generate a report, which is verifiable, and it's contained the measurements on the current program that's running on its like states and also on the hardware itself. So whether it's really running in the TE. This is also very important because we need these primitive to ensure that, okay, this MPC node operator, he is really running the valid MPC node program instead of like making some changes himself. So with this capability, I think a very important immediate things we can do is that we can enforce that, for example, for every sensitive key operation, so an event must be reported on chain so people can check. And this can be enforced if the program is running inside TE. And this is some feature we call transparency log. So with this, you can see actually this almost makes like collusion like impossible, because if they try to do something, they cannot just do something that without expose this to the public. So there is a record on chain for people to check. So this is very important. And finally, I think so why the TE is becoming popular recently is that the Intel TDX, the latest generation of TE, is really easy to use. This means so only if you can Dockerize your application, you can directly get it running inside TE. So there is no, I would say, extra cost for you. For example, you do not need to do extra migration or development things. So then you can directly get the current stack running inside TE. Yes.
Super exciting, yeah. And just a personal question, is that already possible for the TE GPU as well in a similar form, or is that a little bit further away?
Yeah, actually, we have to do the test on the first, yeah, it's totally usable. And second, the performance, we have tried to run some open source AI model inside the TE GPU, so the overhead is below 10%. So I think the performance is also very good. So the only limitation here is that, for example, there is some very big project who wants to run a very big AI model inside TE GPU, which may require more than one graphic card. For example, they will need 8 H200 cards to get their model running. So this is currently impossible in the current TE GPU, but this will be fixed in the next generation of the GPU. So the next generation of GPU from NVIDIA is called Blackwell. So when the Blackwell series is coming, this problem will be solved. Then I would say we will have the fully functional TE GPU at that time.
That's crazy. So, and I imagine interesting, probably the problem set of having multiple GPUs running inside a TE probably is kind of similar to the MPC kind of problem, right? In some way. Yeah. Funny, yeah.
Okay.
Well, cool, yeah. Just sort of aside from maybe the threshold cryptography topic, what are the use cases that you guys are building with TEE, and kind of what are you excited about for TEE specifically? Yeah.
Yeah. So also, for example, we are combining TE to the cryptographic solutions, like I say, for MPC to solve the collusion problem, and some people are running TE to running the ZK circuit to solve the privacy problem. Because if I am a ZK circuit operator, I can see everything happening. So and TE can help bring the privacy to ZK. And also, I think the TE itself it needs MPC or ZK because when T is encrypt like the memory or it's seal its data when it's trying to encrypt the data to the hard disk, actually it's all it needs the keys inside the TE. And now it depends on the hardware-based keys which is generated during manufacturing. And this is a problem because we don't really trust like the centralized manufacturer like Intel or AMD. So one solution to it is that actually we can replace this key with the decentralized infrastructure, the decentralized key management service, and MPC is I think a very important solution to them. So this means, for example, in the ideal world is that we should generate the key with MPC and pass the key into TE, so it can use this key to, for example, encrypt its states. So this will be this is what we are doing. So we call it decentralized root of trust to replace the key management, with the MPC-based solutions. Yeah, and also there is some real-world use case like AI plus TE. So this is very important because, for example, recently there is a project called Tihihi. So it's AI agents. You can visit in the Telegram. You can chat with him. And also there's project like Elisa. So why these AI agents project they want TE is that they want to build the real autonomous AI agents. Because, for example, now the AI agent can maybe own its own wallets, but given the current hardware, actually, when we say AI agents has its wallet, actually this wallet is controlled by the developers, by the human beings. But if we can get the AI agents running inside TE, then this means these wallets it can only be controlled by the AI agent itself. Then it's a real independent autonomous agent. So this is very interesting. This will unlock a lot of interesting use cases. So like, for example, the bots can do all the asset management for you. So there's more interesting ideas to come. So yeah, so this is the recent some use case we are interested in.
Very exciting, very exciting. And just a short shameless plug, there's a company called Polycrypt. Sebastian is also an advisor of them, and they are building what's called a Shatter TEE. So they're kind of combining this, as Sheldon is saying, kind of running the threshold encryption nodes inside of TE. So and it's awesome because, as I said, it's becoming really simple now to do this. Yeah. Great.
I think TEs are nice in the sense for crypto because you can have this two-factor security. Essentially, I think for most of these distributed crypto protocols, they should be actually deployed inside TE just to have double security. Because especially for many advanced protocols, I mean, of course, I like crypto. I mean, cryptography, not cryptocurrencies necessarily, but cryptography. But I mean, many of these protocols are they're very complicated, so they can be you can make bugs when you implement them, and B, some of them are rely also on like, so let's say a bit like non-standard assumptions. And I mean, with the TE, you have essentially double 2 level of security. I mean, even if this assumption fails, you're not completely lost. And you don't lose anything in many cases. Huh? So I think it's really nice.
Yeah, I think the defense in depth aspect is great for TEs. I do push back on like the way that this is all framed as, you know, MPC TEs mitigating the threshold assumption from MPC, but I think as Shelvin mentioned, right, if you put a threshold network, each of the nodes into a TE, it's mitigating both ways, right? The MPC is mitigating a side channel attack on any individual node's TE if implemented properly, and vice versa. So like that's kind of the power of orchestrating multiple pets together. That's like a big part of sort of our thesis around how this is all going to develop, is that at the end of the day, it's not just one thing that's going to win, right? Like there's no point getting tribal around any of these technologies because the end user experience is what matters.
Agreed. Yeah.
I think in any case, kind of distributed cryptography with TEs together works quite well, because in my opinion, like the one thing that can always happen with TEs is that the operator can kind of censor inputs and outputs, right? The operator can always decide what to input into the TE, and what, like, if it doesn't like the output of a TE, it just doesn't forward it. So the solution that you would do is like you would just employ multiple machines with multiple TEs, like kind of let the same thing run, and then hopefully there would be one that is not censoring. So kind of that's, I mean, goes into a similar direction what you do in distributed computation anyway, right? Like you have multiple parties already running, so you just let all of them have a TE as well.
Great. Yeah. Do we have any more topics on the TE? Otherwise, we would ask Sebastian to introduce this secret sharing with snitching concept.
I'll also add, so we have a distributed, like kind of an encrypted distributed database product that we've been onboarding people to, allowing people to do NoSQL calls. And we have a lot of interest in there to do a lot of these LLMs, large models we can support in pure, you know, MPC with that data. And I think that structure has been very interesting to the people we're talking to, where basically they don't want to be putting PII for like long periods of time in with a pure TE trust assumption, right? Where kind of like what happened with SGX.fail, right? If you just get into the TE, you have like historical access to all of the information that was in there. But rather you rely on the TE trust assumption purely at inference time or usage time, right? Compute time. And it's only exposed if somebody has a direct attack, like 0-day attack, and is kind of monitoring it at a specific moment. And we think that is like a very kind of reasonable way to approach the trust assumption there.
Interesting, and this also how it is kind of deemed to be okay to use for MEV for the transaction ordering, to use the TE for transaction ordering, but don't use it for the actual blockchain itself. Like I remember in the past there was actually the Intel built this SGX chain kind of, right, like Sawtooth Lake or something back in 2017. Yeah. So that there was there was already sort of the Intel chain back then. Yeah. Pretty interesting. Okay. But yeah, would love to give Sebastian the opportunity to talk about this paper, about secret sharing with snitching as an alternative mitigation technique for the mitigated threshold trust assumption.
Yes. Okay. Thanks. Yeah. So we have this paper, or it's a research paper that was like published this year at ACM-CCS. And it's like together with some of my co-authors from Warsaw University. And so what is this paper doing essentially is that we looked into this. Most of, like essentially all of this threshold cryptography is based on secret sharing. So this is the first thing that you need to look into. I mean, like how to share actually a secret. There are like techniques from, I don't know, the 80s or 70s when Shamir invented this Shamir secret sharing. And the problem with all of the secret sharing is essentially that there can be like secret collusions. So I mean, like essentially, if we are like these 5 people now, and Andreas can send me, for example, his share, and we have a 2 out of 5 access structure, meaning that we need 2 people to recover the secret, then Andreas could like send to me his secret share, and then I can recover the secret, and with the secret then I can whatever sign stuff. So there can be these collusions, and in particular the problem with we of course also have collusions in or the possibility for collusions in blockchains, right, with correctness. But then if there's a collusion, everybody can notice it because everything is public. So if they all of a sudden start to make a fork or like come up with an alternative or like start to reorder or accept wrong transactions, then at least you know that something fishy is happening. While for collusions, when you are talking about secrets that you want to recover, it's not easy to figure out that there was really a collusion, right? So because everything happens secretly, so Andreas can just send me this over a private channel, and then I can recover the secret. So it's much harder to prevent collusion in for secrecy or privacy applications than preventing collusions for correctness, like in consensus schemes. So what we looked into, how can we actually de-incentivize such collusion, and then we came up with this new notion of secret sharing or secret sharing with snitching, where we essentially add to this secret sharing scheme. So normally in secret sharing you have a reconstruct and a share procedure. So a share for sharing the secret, and the reconstruct then where you can reconstruct the secret from the shares. And we add like some new algorithms there or protocols, and it's like called punishment essentially, or snitch. Or snitch is essentially one routine, and the punishment is another one. And essentially, we give each of the shareholders the opportunity to snitch as soon as there is some collusion. So if Andreas comes to me and sends me some information about his secret share, then he then I have the chance to snitch on him and say that, okay, Andreas was actually the person who tried to collude to me, and I can essentially then punish him with a proof of misbehavior, or of proof of collusion, or proof of misbehavior. And so I mean, like this is nice. So a naive solution could be, okay, I can say Andreas, as soon as I see Andreas' share, then I can use Andreas' share and send this maybe to a smart contract, and then I have a proof that Andreas actually colluded to me because he sent me a secret share. But this is of course not like this is of course one type of attack that Andreas can do, but Andreas could also do a completely different attack. And for example, he could just say that, okay, let's run an MPC protocol together and do some illegal stuff with our shares. For example, signing a message or encrypting like an encrypted block prematurely. Okay, and this is much harder to prove, or even impossible to prove. And that's why we introduced some new concepts in the secret sharing, which we call MPC hard functions, where essentially we make sure that in order to reconstruct the secret, you actually have to evaluate a function that is difficult to evaluate in MPC. So in other words, if Andreas and me collude, then either we have to evaluate this MPC hard function in a distributed way, but this is impossible, or it takes a super long time, or he will send me essentially sufficient information so that I can actually do this recovery or this reconstruct alone. If I can do the reconstruct alone, then I can always extract this a proof that Andreas was colluding with me. So this is kind of like in a nutshell what we are doing. So we come up with a construction for this, secret sharing with snitching, and prove its security, because in cryptography we always want to make security proofs and security models. So we prove its security, and then so now we are currently extending this to multiple ways. We want to have more efficient schemes for this. We want to like even have a stronger security, because the first construction that we had didn't offer security against some very advanced attacks that we ignored in our first paper. And then in particular, what we want to do is like coming up with applications also for this MEV stuff. So like kind of batch decryption, like a batch decryption like scheme, where you can like similar to what Shutter is doing, where you can decrypt many transactions, or many or you can like there are like many secrets are shared. Like you can think of this as the transactions, right? These are the secrets, and then you have many of them are shared, and then you do like a batch solving of all of them. So then you could potentially use this in something like as an MEV countermeasure, and which has this feature that you cannot collude, essentially. Or if you collude, you always risk that you get punished.
And would you say then it turns the problem from a distrust assumption problem into an economic problem, basically, and then it's about the stake, kind of the side of the stake?
Yes. I mean, essentially, it's like this. That I mean, parties would then essentially, I mean, shareholders or parties that have a share of the secret, they would lock some stake, and if ever there's a proof of misbehavior sent by any of the other shareholders, then you're gonna destroy the stake, or like give it to whoever is, I don't know, you distribute it among the other honest shareholders or whatever. So it's becoming an economic problem. Of course, it's like a question how much stake people have to lock, right? Because for MEV, maybe you earn like 2 billion euros by doing this front running, then it will be difficult, I guess, to convince stakeholders or like shareholders to lock 2 million of dollars. But yeah, so this is.
I was going to say it's very non-trivial. This is some work we did a while back for similar reasons, trying to figure out how to mitigate these things. We were trying to reason around pricing secrets, and what we finally came to is that if you have arbitrary secrets being put in, so for MEV that's not true, right? There is like some way to price it because you have a feed of like what the possible things are happening inside. There's some profit. But then the minute you get into arbitrary secrets, PII, things like that, it becomes sort of, you just put your finger in the air and decide on a number that sounds big, right? It's kind of the best that you can do.
But there's always a problem with game theory, right? So you always have to figure out what are the utilities, and this is a very difficult part in game theory, and everybody criticizes this game theory for this, essentially, or crypto economics, I mean, whatever you call it. But how do you actually evaluate? Because some people can have completely different utility.
Totally. One thing that this, so I read this paper when it came out. I think it's really cool, and we have been also thinking about similar things. But it brings up one of the problems I think with this whole space, which is it's like an Ouroboros. We're all eating our own tails here because you mentioned MPC hard problems, right? But then if you collude inside of a TEE, you're creating the same kinds of problems. Like all of these pets actually make it easier to coordinate without trust even, and we're putting more walls in front of each other, and then also at the same time creating technology that makes it easier to use, more efficient to coordinate without doing that. And it is a little bit disheartening that it feels like that's kind of inevitable, like we're going to always keep repeating that cycle, and at the end of the day there's some amount of foundation that is going to come to this threshold assumption, right? Building the actual trust set.
Yeah, that's interesting. Kind of it's definitely sort of an arms race in some way on all sides. Yeah.
I mean, I think it's nice if it. I mean, first of all, we are looking if it's actually possible to do something like this. It was not. I mean, it's difficult to do anyway from a theoretical point of view. But yeah, you have to for sure like figure out what is the price of the secret, as Tristan said. I mean, this is very difficult. I think. I mean, I have no clue how to evaluate the price of the
Well,
secret.
imagine for medical data, how much?
Yeah, actually, that's for problem. Or I think also like for. I mean, like,
it?
but I think for other types of data, I guess also for like financial
Yeah.
data. For financial data, it's probably easier. So that's good because we're in the blockchain space. Everything is about finance. So you can. But even there, I think the problem. I mean, for my opinion, for MEV countermeasure, it's kind of difficult because I mean, like, suppose you like say, I mean, how much money would you say you lock into this? I mean, like how much money the shareholders have to stake? I mean, you cannot ask them to stake 1 million. Makes no sense, right? So, but then sometimes there could be MEV opportunities of 1 million. I guess I don't know if it still exists, but at some point I saw this kind of graphs where there's an opportunity where you can earn like 1 million of by doing some front running. So then
there are some tools that make this easier, things like restaking. If you make access to kind of locked up capital, you can offer additional yield, but it's already productive. Like you can get higher amounts of capital locked in, provided that they're willing to take on the risk. They trust themselves or whatever the operator they're using is. But yeah, I think it is not an easy problem. And what we sort of came to in the end when thinking about this problem is that it really is going to end up requiring applications to do the very hard work of this, because it's based off of the specific data that you're putting in, who your users are, and how much you think that the kind of parties would be willing to pay for breaking the security. For MEV, I think it's particularly interesting because there is this is a better mechanism because it happens, during the collusion, and actually creates more coordination friction, right? Which I think is better than doing it the other way. But with MEV, you could, this stuff is accountable, right? If I send it through the MEV supply chain and it gets front run and it wasn't supposed to, right? Then I can complain, and there are ways to sort of make the whole system accountable, or even in the net, you can look at long strings of blocks and do some sort of statistical analysis on this, and use that as build a proof around that, and have slashing built into that. But yeah, that all of that sounds less good than if we can actually do it, kind of create increased coordination friction during the actual collusion process.
I mean, this actually,
I think sorry.
This is actually a good point. I mean, maybe we don't even need to exactly have put the amount of money, or evaluate how much the price of collusion is, or how much you will lose in money, how much the price of such a collusion is. Maybe it's sufficient actually that you can at least, you can show that there was collusion. So then you know that the system is somehow compromised, and then you need to do something. Because at the moment, we cannot really do this with any of the secret sharing or threshold-based crypto. We can never know if there was actually collusion or not, because we can simply not prove it. So at least this gives you this is what you mentioned. I don't know if you really meant this, but this gives you this accountability.
No, I do, and it adds, and this is the reason I'm particularly excited about this field of work, is that it adds a sort of new incentive mechanism, which I think is actually quite powerful from a game theoretical perspective, which is, instead of thinking about the system as compromised or not compromised, there are shades of gray where now you can be a sort of good actor in the space, but still solicit collusion with other people in the space, trying to get them to trust you. And then, you create sort of a vigilante system within your own threshold set, which I think is an interesting thing to reason about from a coordination perspective.
Definitely, yeah. I think what I think it would be for just to maybe answer to Sebastian. So I guess you can't prove collusion, but you could prove there was front running, then there had to be collusion.
Maybe I can quickly add. I think especially for MEV, I agree. It depends very much on the application, but I think especially MEV is an application where all of these anti-collusion mechanisms work very well, because at least if you consider encrypted mempools, then the colluding parties don't know before colluding what would be their profit, right? They don't know what the transactions are that they are decrypting, for example. So they don't know how much MEV can actually extract. So they have to collude before knowing what the profit they can make, but then they take the risk of potentially losing their stake when they might not even make a lot of profit with the collusion.
That is mostly true, but that is not strictly true, because you can know based off of actions in the last block, and let's say, for example, centralized exchange rates, if there's massive movement in between, you can know that there are opportunities in the next block that you want to be able to play with, because you're one of the stakeholders there. But yeah, I think it mitigates a lot of
Yeah, I think, for sure there's some information you can get, that's true, but you can't exactly quantify necessarily the amount of profit that you actually make. And then it's a matter of, do I take the risk of colluding and potentially getting slashed for?
That's this whole, again, that's why I think that this whole exercise is interesting. And we have up there mitigating trust assumptions. Look, TEs are not perfect either, right? They're I see all of these as ways to, add some defense in depth, as you're mentioning, obstruct the kind of pure EV analysis of how much I would make if I do this, which then makes you more the more uncertainty there is, the less likely that is, and then also increase friction to collusion. And if you can kind of do those more and more, eventually you get to something that is pretty secure.
Yeah, although I think T is very useful, but actually at the first day we begin to use it, we know T is not a silver bullet to all the problem. And also, more importantly, also like we have discussed this with the Flashbox team, and we all agree that T, for them to correctly use T is not a very easy job. So this is the idea behind. So for example, why we are writing many docs, articles about it, why we are doing the SDK and provide some services for it. I think all of these is to show to the world like what's the I would say best security best practice of using T on this. And honestly, I think if with like correctly configuration and also with very secure like review on the whole system, actually I think that the security level for T can be very high, even like given like all these vulnerabilities we are already known. Yeah.
Exciting stuff. I think there's no questions from the audience, or I can't use this thing. But yeah, if no one else has any more questions, we can also wrap it up. And from my side, thank you everyone so much. I think this was super interesting. I think that again, these puzzle pieces is super interesting, how this all fit different types of cryptography hardware, and then also I guess crypto economic mechanisms, how they all fit together. We can finally see how this is evolving. I think just a couple of years ago all of this was pure theory, but now this is now actually people are using it, and will be even more. Personally very excited about seeing autonomous agents run on distributed sort of MPC autonomous agents inside TEE. That would be very interesting. Yeah, but thanks so much for all your input. And yeah, encourage everyone to read into these all the projects and the secret service snitching blog post and all the work that you guys are doing. Yeah, and everyone feel free to add some closing thoughts or shill what you're building, or yeah.
Yeah, I would add closing thoughts that it's just like you mentioned, intersection of crypto economics, cryptography, and hardware security is important. But I think that, like I mentioned before, a thing that people need to keep in mind is that all of these are tools for programming trust. And unlike in blockchains where, if you're running your own node, well, I guess it's not unlike, because if you're running everything locally, then that's the same kind of security that you can get from a blockchain if you're running your own node, right? But if you're not running everything locally or as a party in an n-event threshold or whatever, then you are still moving trust around, putting walls in the way, increasing friction for bad guys, all that stuff. But there is always going to be some amount of trust. And I think that that's a thing that, hasn't been looked upon well in the space, but we are now building tools to make that a legitimate way of kind of creating security. And I think that's like one of the things that I would challenge people to kind of think through more, is that it's not bad necessarily to be distributing trust. That is a legitimate way of achieving decentralization.
Well then, thanks everyone. Have a good rest of the day.
Thank you.
Thank you.
Thanks, everyone.
Bye-bye.